All right, hello and welcome. This can be our lecture video for March 30th. We're going to be talking about exact trig today. Let's look at our learning objective. Our goal is to be able to use our special triangles to find the value of trig functions of angles all around the unit circle. Why are we doing this? By using our special triangles, we can get exact values. And let me just start right now by getting out my calculator, and you should do the same. Also, hopefully you have your notes out with today's date and you're ready to take some notes on this stuff. I think this is actually a pretty important lecture. You can find trig values right now. It's very easy. You've got your sine, cosine, tangent buttons right here. If I asked for something like the sine of 60 degrees, you just plug in sine of 60, press enter, it's going to give you a value. Now, if I said sine of 60 degrees, you'd want to double check that you are in degree mode by pressing mode first and making sure that this says degree right here. We can take the sine of some radians pretty easily. You just flip it over to radian measurement. And if I said, well, let's find the cosine of pi over 3 radians. Now I'm in radian mode. And that one actually ends up being exactly 0.5. So we're at the point where we can easily take the trig value of different angles. But today I want us to really impress why it is 0.5. And then also with answers like this 0.866025, I want to write that as an exact number, and that's going to take a square root. Well, figuring out that square root is kind of tricky, and it relies on our special triangles. And I want to show you guys why angles over 90 degrees make sense today. So although this part is pretty easy, just plugging it into your calculator, the rationale behind why these trig functions evaluate to these different numbers is super important for understanding things like graphing and other more complicated concepts in trig. So that's really what today's about, is getting exact values and building really comprehensive understanding for why these things make sense. So when I say find sine of 30, we saw that you can plug that into your calculator, it spits out a number. If I plug in sine of 30 into my calculator and I make sure I'm in degree mode, it should spit out 1/2. What does this 1/2 mean? Where is this number coming from? So the first thing that's really important about trig is that sine, cosine, tangent, they only work on right triangles. Very important point. If you've got a wonky scalene triangle, we can use some trig on this, but the very first step of that trig is to split it into right triangles so that we can use sine, cosine, and tangent. So sine, cosine, and tangent only work on right angles. All right. If we know one angle is 30 degrees, the other must be 60 degrees because the third angle has to be a right angle. So if we know that this is a right triangle with a 30-degree angle, the other angle must be 60 degrees. All right, our third point is that all 30, 60, 90 triangles are similar. And I'm talking about the geometry word similar. This means the ratio of side lengths is the same. All right, so all 30, 60, 90 triangles are similar. The ratio of side lengths is the same. So if I draw a small 30, 60, 90 triangle here, that's my 30, that's my 60, that's my 90, and a really big 30, 60, 90, even though the lengths in this bigger triangle are going to be much longer than the lengths in this smaller triangle, the ratios are the same. All right. So we're getting closer. The side opposite the 30 degree divided by the hypotenuse, maybe I should say side length. The side length opposite the 30 degree divided by the hypotenuse will always be 1/2. All right, so let's go back to these triangles I've drawn here. This side length here divided by this side length here, even though this one's much shorter than this one over here, this ratio here of opposite over hypotenuse is always going to be 1/2. All right, and here I'll label the opposite and the hypotenuse in this one as well. And we knew to do opposite over hypotenuse because of SOHCAHTOA telling us that sine is the ratio of opposite to hypotenuse in a right triangle. Okay, so when I say sine of 30 degrees, I'm talking about this ratio right here. Okay. Now, we're going to have to kind of get a little bit tricky, because with that previous definition, you shouldn't be able to take the sine of an angle greater than 90 degrees. It shouldn't be possible. But what happens if I plug sine of 330 into my calculator? Let's just see. Okay, first I'm going to make sure I'm in degree mode. And then I'm going to do sine of 330. And it gives me an answer. It says -0.5. So it shouldn't be possible, but my calculator's giving me a real answer. And the reason it shouldn't be possible is that the interior angles of a triangle should add up to 180 degrees. And for us to use sine, one of those angles has to be a 90. So if we let another one be greater than 90, then we've already exceeded that 180 degree maximum, or, well, it's not even a maximum, it's a guaranteed 180 degrees. But it's still possible. So even though it doesn't seem to make sense, we're going to try and draw a triangle, a right triangle with an angle of 330 degrees. So let's start with that right angle, just like this. So there's my right angle. And now here's my opposite side length. I've got to draw the hypotenuse, but first I need to rotate the hypotenuse 330 degrees. So that's 90 degrees there, 180, 270. I almost make a full revolution. And here's where my hypotenuse ends up. So this is a really strange looking triangle. Most people would say that this is not a triangle, but if you're willing to accept that this is a triangle, then I think we can take the sine of 330 degrees. All right, it's a triangle in the sense that it has three sides. They just don't all meet up into a nice shape. So here's what we're going to do is we are going to allow for a negative side length to connect this triangle. So this is a negative side length. All right, and that's why opposite divided by hypotenuse ends up being a -1/2, because this length here is negative. Hypotenuse will always be positive. There's a way to think about a negative hypotenuse, but it's never useful to do it that way. It's always better to think about the opposite and the adjacent being negative. So the reason that sine of 330 degrees equals negative 0.5 is because we have a negative side length for the opposite being divided by our hypotenuse. Okay, let's do some more problems. At the beginning of pretty much all of these problems, it's useful to sketch our special triangles. There is the 30, 60, 90. So you got to draw a little bit squished triangle. And then there is the 45, 45, 90. It's supposed to look more like an isosceles. No, if you're willing to believe that that's a 45, 45, 90, I think we can keep going. All right, and here is the thing. The side lengths of the 30, 60, 90 are 1, 2, and the square root of 3. I think that's a really easy pattern to remember because it just goes 1, 2, 3 with the square root. So 1, 2, and the square root of 3. But we got to figure out which side is which. Well, the shortest side should be the 1. That makes sense. But now this side's longer, but which of these numbers is longer? Is 2 or the square root of 3 longer? Well, actually 2 is longer than the square root of 3 because the square root of 3, if you plug that into your calculator, is equal to about 1.7. So this helps me remember how to fill this in because I know I can look and see this side length here is shorter than this side length here. Now I just have to remember which is the smaller number, 2 or the square root of 3. Square root of 3 is about 1.7. So now this just sort of looks right, that this is 1, that looks like about 1.7, that looks like about 2. All right, and then the 45, 45, 90, this is just 1, 1, and the square root of 2 is one option for how to label it. This is the simplest way to label it. And the Pythagorean theorem helps me remember this one because 1 squared plus 1 squared would be 2. So I need this to be 1 squared to be equal to 2. So square root of 2. Students seem to struggle less with that. And then there's also the triangle that's not really a triangle, the 1, 1, 0, 90, 90, 0 triangle, which I had a student write me an email claiming that this triangle does not exist, but I just showed you a triangle with a negative side length, so hopefully you're willing to accept a triangle that has a 0 length side length. In order to expand our trig and keep all of our formulas consistent, we have to be willing to accept that triangles can have negative and 0 side lengths. Okay, so first off, let's get an approximation for this, and then we're going to try to be more precise. What is the tangent of pi over 3? And you should be able to tell right now that this has to be a radian measurement. 1, because we don't see the little circle indicating degrees. And 2, most all radian measurements include pi somewhere in their measurement. So here we go. I'll get on my calculator. I'm going to switch over to radian mode. And then I'm going to do the tangent of pi over 3. 1.732. Is that what we were asked to do? Pi over 3? Yep. 1.732. Okay. So that is an answer, but it's only as precise as the number of decimals we're willing to copy down. If we use our unit circle, can be more precise. This will, no matter what, this is going to be an approximation because we'll have to stop writing the decimals at some point, even though this is an irrational number. All right, so here's what we're going to do. We are going to start by drawing a right triangle with a pi over 3 angle. In pi over 3, let's just convert that into degrees real quick. I do like working with degrees pretty frequently. All right, so to convert any radian measurement into degrees, we multiply by 180 over pi. The pi's cancel out. 180 divided by 3 equals 60 degrees. All right, so this is, let's draw a right triangle with a 60-degree angle. So I like drawing my right angle first, and then I'm going to draw my hypotenuse rotated 60 degrees up from the adjacent here to come meet the opposite. So there's my 60, there's my 30. Well, this is one of our special triangles. And since all 30, 60, 90s are similar, we can just use the side lengths that we've memorized, which are 1, 2, and the square root of 3. All right, from our reference angle, so this is our reference angle, the one that's we're asking about. So we can even draw a little person standing here. Looking out, this side over here would be my opposite. This side here would be my adjacent. And this side right here would be my hypotenuse. Now, if I go back to SOHCAHTOA, the tangent of an angle should always give me the ratio of the opposite over the adjacent. So tangent of pi over 3 equals opposite over adjacent. And even though I don't know what the opposite and the adjacent are, I know that the ratio between them should match the ratio shown here in my special triangle of the square root of 3 over 1, which simplifies to just be the square root of 3. You plug in the square root of 3 in your calculator, you're going to get this exact same number back. But this is a more precise answer. To write the square root of 3 preserves all of the precision of this number. All right, I think we will put, let me just check my next slide. I think we can do one more slide and then I'm going to pause this video. All right, try all of these in your calculator. Sine of 30, negative 330, 390. Let's see what's happening. Okay, so those are all degrees, so I'm going to switch back to degree mode. All right, sine of 30, I get 0.5. All right, sine of negative 330. I also get 0.5 for that one. All right, sine of 390. I get 0.5 again. Sine of 750, 0.5 again. Sine of negative 690, what do you think? Yep, it's 0.5 again. So all of these equal exactly 0.5. All right, what is going on here? Why are all of these giving me the same value? Is the sine of any angle just always 0.5? You can try a different one, you'll get a different answer. But all of these have the same value. And that's because all of these angles are coterminal. So here's what we're going to write for this. Coterminal angles have the same trig values. So we can draw a triangle with a 390-degree angle. You just start with your right angle and you rotate around 390 degrees and then you connect that hypotenuse over to your opposite. Well, what we've done is we've drawn the exact same triangle. It's just a 30-degree triangle. So this here is equal to a triangle where we rotated that hypotenuse just directly here. All that matters is where the hypotenuse ends up. So all coterminal angles have the same trig values. Okay, this would be a good spot to stop.